In this video, we're going to discuss the reactivity of acids and bases. Acids and bases are hugely important for understanding biological chemistry. By understanding what makes a strong or a weak acid or base, we can also learn a lot about other types of chemical reactivity. First, some basics. An acid is a molecule that can release a proton, so a hydrogen cation. A base is a molecule that can bind to a proton. By definition, these sorts of reactions are always reversible. In the example here, we have something that is an acid because it has an acidic proton, a proton that is easily released. When it releases a proton, this reaction also creates a so-called conjugate base. As this is an equilibrium, there is an equilibrium constant Ka. Ka is defined as the concentration of the conjugate base multiplied by the concentration of protons divided by the concentration of acid at equilibrium. You may have heard of something called a pKa. pKa is minus log of the equilibrium constant. We use pKa as a measure for how strong an acid is. The lower the pKa of the molecule, the stronger an acid is. There is also pH, which is a measure of acidity, not of a compound, but of a solution. pH is the minus log of the concentration of protons. The lower the pH is, the more acidic a solution is. When we look at acid-base equilibrium, we have an equilibrium between an acid and the conjugate base. We can plot this in a graph in terms of energy, so that there is a starting material, that's the acid, and then there is a product, that is the conjugate base, plus a proton. These two situations have different energies. It's this difference in energy that tells us the position of the equilibrium. The larger the difference in energy, the more the equilibrium will be on the product side. The relation between energy and equilibrium constant is defined in this equation. The difference in Gibbs free energy between the two situations, delta G, is minus RT ln K. R is the universal gas constant, T is temperature, and K is the equilibrium constant of the acid-base equilibrium. The larger the difference in Gibbs free energy, the larger the equilibrium constant is going to be. The question then becomes, how do we make for a larger or smaller difference in Gibbs free energy? Essentially, you can make this difference larger by either increasing the energy of the starting material or decreasing the energy, so pulling the starting material up or pulling the product side down. How do you do that? By something called stabilization. You can either destabilize the starting point, which means increasing its energy, or stabilizing the product, and that means decreasing its energy. In the current example, there is a mechanism that leads to stabilization of the product. The conjugate base is an anion. Because of its molecular structure, this anionic charge can be distributed over several atoms in the molecule. This is a process called resonance. We've seen that in one of the previous lectures briefly, and it leads to distribution of charge, smearing out of this charge density over a larger area, if you will. This is a stabilizing effect, so it leads to a lowering of the energy of the product, and therefore a widening of the energy gap, leading to a larger equilibrium constant. This effect is clearly visible by comparing, for instance, acetone, the bottom compound here. What you can see there is that our acid has a considerably lower pKa than acetone, making it a stronger acid. Why is that? In our acid, the anionic charge is smeared out over a larger part of the molecule than for acetone, widening the energy gap.